Hello, welcome again. Welcome to part 3. And in part 3, we are going to study the heat equation. So let me recall the heat equation. It's ut minus Laplace u is equal to 0. And if I assume that u does not vary with time, then this ut, the derivative of u with respect to t disappears. So that's the stationary case or the equilibrium case. It just degenerates to the Laplace equation. Okay. So you have just Laplace u is equal to 0 and u is going to be independent of time. So ut is equal to 0. Okay, so now let us consider the following problem, which is ut minus Laplace u is equal to 0 in Rn cross 0 infinity. And u at time t is equal to 0 is a function f of x. So this you can view this problem in the upper half plane, in which the base is Rn and the z is the time variable, and it's the infinite time. Okay, so it's 0 infinity. You can also study the heat equation in bounded domains. So in which case you can actually consider this domain we call this as a cylinder, an infinite cylinder. Or you can also study with bounded time, in which case you have a bounded cylinder. Okay, but here we are going to study in the case of the infinite or the upper half plane. And so what we have is we have ut minus Laplace u is equal to 0 in Rn cross 0 infinity. And at time t is equal to 0, u actually takes the function f of x. Okay, so we call this as an initial value problem. Okay, you may already be familiar with this. And what we want to do is we actually want to find a solution to this problem. Okay, so how do we go about finding a solution to this problem? So let me define something called the heat kernel. Okay, so let me define a function k of x comma t, which is now let me emphasize this. So this is defined in Rn cross open 0 infinity. So this is 1 over 4 pi t to the n by 2 e power minus mod x squared by 4t. So there's a Gaussian part, which is e power minus mod x squared by 4t, and then you have this 1 over 4 pi t to the n by 2. So therefore, as such, this kernel is not defined when t is equal to 0. So that's something that you need to keep in mind. So this is what is called as the heat kernel, and this has some very nice properties. So one of the first properties that we will study is the following, that the heat kernel actually satisfies or solves the heat equation in Rn cross 0 infinity. Okay, so I want to show that k is a solution to ut minus Laplace u is equal to 0 in Rn cross open 0 infinity. For any time t positive, it actually satisfies this, satisfies the heat equation. Okay, so how do we go about the proof? The proof actually follows by computation. Okay, so let's differentiate k with respect to t. So therefore, I use product rule combined with chain rule. Okay, so first I need to differentiate this 1 over 4 pi t to the n by 2. So that explains this minus this part over here. And then I retain this. So this is e power minus mod x squared by 4t plus. So now I differentiate this e power minus mod x squared by 4t. So that explains this part. And then I retain this. Now I can take the common terms, which is e power minus mod x squared by 4t. I can also take this 1 over 4 pi t to the n by 2. So when I take this common, what remains is I also have this 1 over 4 pi t in the denominator. That's an extra factor. So the 4 pi, they cancel away. T is in the denominator, this negative sign. So I get minus n by 2t plus what remains here is mod x squared by 4t squared. So I have dk by dt is equal to this expression. Okay, now let me also differentiate the k with respect to each xi. So I take the ith partial derivative of k, but the computation or the partial derivative of k with respect to xi is easier because x is only present over here. So this is independent of x. Okay, so what we get, so this 4 pi t to the n by 2, that remains 1 over 4 pi t to the n by 2, that remains. You have e power minus mod x squared by 4t, that remains. And then I just need to differentiate this with respect to xi. So you get minus 2xi by 4t. That's it. Okay, now because I need to consider the Laplacian, let me also differentiate this quantity with respect to xi again. So when I differentiate this with respect to xi again, so I get d square k dxi square. Okay, so now in this case, you need to use product rule. Okay, combined with chain rule, of course. So this 1 over 4 pi t to the n by 2, that's going to be common. So you have e power minus mod x squared by 4t, and then this differentiates again. This part differentiates again. So you get 4x squared by 16t. Actually, you get minus 2xi by 4t. And then you need to multiply with this minus 2xi by 4t. So that explains this 4x squared, xi squared by 16t square. And then you need to use, you need to differentiate this. So you get minus 2 by 4t times this factor. So this is what we have. So now, okay, you can also take, you can simplify certain things. We can 4 and 16, they cancel away. This 2 and this 1 by 4, the 2 factor cancels away. And then what I need to do is I need to take the sum, d square k by dxi square from I is equal to 1 to n. So when I take the sum, okay, so this e power minus mod x square by 4t, that remains. 4 pi t to the n by 2, that also remains. This 4 and this 4, so 1 over 4t square is in the denominator, and xi square is going to give you mod x square. Okay, so here again, this e power minus mod x square by 4t, and then 4 pi t to the n by 2, they remain. And so here you get minus 1 by 2t, but that's summed n times. So when I sum it n times, I get minus n by 2t because corresponding to each I. Notice that this is dependent on I, this is independent of I. So you get minus n by 2t. Okay, all right. So we have this, this is Laplace k. And now let's go back. And what was it that we derived for dk dt? This is exactly what we have here. So now notice that dk dt minus Laplace u is equal to 0 in Rn cross 0 infinity. Now, I define this heat kernel, and it may look mysterious at first as to how you actually come up with this. There is nothing mysterious about this. So the heat kernel can be arrived by using Fourier transforms in the space variable. And what you do is then you actually convert this into first order ODE, and then you actually solve it. Okay, so I don't want to get into this. So the expression for the heat kernel can actually be combined. So it requires two things: solving an ODE and then also using Fourier transforms. Okay, so let's not get into that. We will just assume that it is true, and that this is the heat. This is what we get when I use Fourier transforms combined with solving an ODE, and this is what we get. This k of xt is 1 over 4 pi t to the n by 2 e power minus mod x squared by 4t. Okay, now before I get to one of the important properties, one thing that I want to show is that the integral of k of xt. So you take any time slice, t, of course, t positive, you take any time slice. You want to show that the integral of k, okay, on that time slice, that's actually equal to 1. So this is going to crucially enter into the picture later on. So let's actually show this. So how do we actually show this? Okay, so the proof is actually not very hard. So we have, okay, what is k? K is 1 over 4 pi t to the n by 2, and then you have this e power minus mod x squared by 4t dx. Okay, so this is integral over Rn. Okay, so now what I want to do is, let me just change the variable. So let me consider x by 2 root t is equal to y. So if I change this variable, then what do I have? Now, as x varies over Rn, t is fixed for the discussion. So y also varies over Rn. So therefore, the integral is still over Rn. So then you have e power minus mod y square. And then now you just need to consider the determinant of the Jacobian of the transformation. So because I have x is equal to 2 square root ty, so when I consider the determinant of the Jacobian of the transformation, so it's going to be a diagonal matrix. So therefore, the determinant is going to be 2 root t to the n. Okay, so therefore dx is converted to 2 root t to the n dy. Okay, so now this 2 root t to the n, so this is independent of y, so you can actually take it outside the integral. Okay, so therefore you get t to the n by 2, so that cancels away, t to the n by 2, and there you also have this 2 to the n, and now you have this 4 to the n by 2, which is the same as 2 to the n. So therefore this 2 to the n and this 4 to the n by 2, they also cancel away. What remains is 1 over pi to the n by 2. So now it's a standard result. You may be familiar with this, that the integral e power minus mod y squared dy is actually pi to the n by 2. And the proof of this is actually not very hard. So you actually convert this into a set of 1D integrals, and then you actually convert this for, you actually do this for each y1, y2 up to yn, because e power minus y1 square all the way up to yn square is e power minus, e power minus y1 square times e power minus y2 square, so you have this the splitting, and therefore what you can actually do is you can convert this into 1D integrals, and in 1D integrals you have square root of pi, and this multiplied n times, so you get pi to the n by 2. So we have pi to the n by 2, and this is actually what we wanted to show, because this e power minus mod y squared dy is pi to the n by 2, and that cancels away this with this pi to the n by 2. So therefore this integral of the heat kernel integrates to 1 for each time slice t. Each time slice t. So therefore we have the result. Okay, now what I want to do is to show the following, that we just so we show that in the complement of, so you take, again, you fix t is fixed. Okay, and what you do is you consider a ball of radius r centered at 0. Okay, so t is fixed. You consider the ball of radius r centered at 0, and then you consider the complement of the region, which is Rn minus Br of 0, and then you integrate this k of xt dx. Right? Now this is true for each t. So now what we do is you take t smaller and smaller and smaller, and then what we actually observe is that the limit as t goes to 0 from top, that's actually equal to 0. Or in other words, if you look at the function has a very, very big peak near t is equal to 0, but in the neighborhood of the origin, in a small neighborhood of the origin, if you consider the complement of it, then the area is actually quite minimal. So therefore, as t approaches 0, therefore the peak gets bigger and bigger and bigger, and the neighborhood of the origin, the area gets smaller and smaller. So therefore, in the limit, what we have is that as t goes to 0 plus, if you take out a small neighborhood of the origin, and then you consider the area or the volume outside of it, that actually approaches 0. So that's the content of this statement. Okay, now why is this true? Okay, so here again the proof is not hard. So R is fixed. You take any R however small, it doesn't matter, but R is fixed for the discussion. And t is fixed, but then you let t start varying for the same fixed R, and then as t approaches 0, then the volume outside of the ball of radius R, sorry, the volume surrounded by K, okay, outside of the ball of radius R centered at 0, that's going to be equal to that's going to tend to 0. Okay, so again, so what we observe is the same set of the same Jacobian, or the same change of variable that we saw earlier. So let's do the same thing over here as well. So if I consider Rn minus Br of 0, k of xt dx. Okay, so if I change the variable, so what was the change of variable? It was this: x by 2 root t is equal to y, and so x by 2 root t is equal to y. So then what we have? So what we have is, so we have 1 over pi to the n by 2. Now so earlier it was just integral over Rn e to the minus mod y square dy, but now what we have is, because I have taken off the ball of radius r centered at 0, we get Rn minus b r by 2 root t of this integral, e power minus mod y square dy. Now, what we observed in the previous step was that the integral over Rn of e power minus mod y square dy divided by pi to the n by 2, that's actually equal to 1. That's actually equal to 1. Okay, now observe this. So because that's actually equal to 1, it's a finite number, right? Now, this is going to be the remainder term. This is going to be the remainder, or this is, you can think of this as the tail of the sequence, so the tail. Now, because this actually goes to 1, as t gets smaller and smaller and smaller, you see that this t is actually in the denominator. Therefore, whatever you have taken off, right, this br by r is fixed. So br by 2 root 2, that radius gets bigger and bigger and bigger. So therefore, now what you have is the tail. The tail has to go to, it gets smaller and smaller because the integral over Rn, that converges to 1. So therefore, what we have is that limit as t goes to 0 plus of Rn, and then you subtract out br of 0, because this is the same as this. Now, as t approaches 0 from top, this actually goes to 0. So therefore, what you have is that the volume enclosed by this k, okay, between this and the base, right, that the area, or sorry, the volume outside of a ball of radius r, that is actually very, very small in the limit. Actually, it's actually in the limit, it's actually is equal to 0. It's actually equal to 0. So this is also an important observation. Now, my goal now is to give an indication. So you may have heard this term, infinite speed of propagation, for the solution to the heat equation. So what I actually want to do is to show this. Okay, what we mean by infinite speed of propagation for the solution to the heat equation. So we in fact prove the following theorem. Okay, so the theorem is the following, that let f be a bounded continuous function. So the initial value problem, that initial value, I assume f to be bounded, and let me define u of xt as 1 over 4 pi t to the n by 2 integral over Rn e power minus mod of x minus y the whole square by 4t f of y dy. Now, people who are familiar with convolutions, you will observe that this u of xt is actually the convolution of f with the kernel, but in the space. So t is fixed. So the convolution of f with the kernel in the space variable. So therefore, that explains this minus of mod of x minus y square. Okay, f of y dy. Now, what this theorem tells is the following, that if you consider this u of xt, then it shows there are three parts to this theorem. One part is that u is actually smooth in Rn cross 0 infinity. Okay, and the second part is that u actually solves the heat equation, and the third part is that in the limit as t approaches 0 plus, it actually satisfies the initial condition. So therefore, what I need to do is, first of all, show that u is smooth. Second of all, show that u satisfies the heat equation. And the third part is to show that it satisfies that as t approaches 0 plus, u of x comma t limit as t approaches 0 plus is actually equal to f of x. So we have to show these three parts. Okay. Now we prove this theorem and then explain why this explains the phenomenon of infinite speed of propagation. Okay, so I haven't quite defined what infinite speed of propagation is. I will give a loose definition, and we will see why this theorem explains this phenomenon that you actually observe, that we actually have seen. You may have seen this before. You may have heard of this term before. Okay, so we need to show that. So first of all, so why is it that u is smooth in xt? Okay, so what is it that I need to do? What I need to do is I need to show that all the partial derivatives, not only in x, but also in t, all the partial derivatives exist and they are continuous. So therefore, that would show that u is actually smooth. But remember, there is this exponential part. So as a simple case, let's say I differentiate this with respect to xi. So if I'm going to differentiate this with respect to xi, what I would actually get is you get this e power minus mod x minus y the whole square by 4t times now some xi minus yi. Okay, so now if I'm going to take higher and higher derivatives of u with respect to xi, what I'm actually going to get is you're going to get e power minus mod x minus y the whole square by 4t times some polynomial in xi minus yi. Xi minus yi. But you see that there is this exponentially decaying part. So all this polynomial times the exponential decaying part, because you have the fact that you have this exponentially decaying part, you still get integrability. So therefore, all the partial derivatives, and it doesn't matter whether you consider the derivative with respect to x or whether you consider the derivative with respect to t, because of this exponentially decaying part, you actually have that all the partial derivatives exist and they are continuous. Or in other words, what you can actually do is you can interchange the integral and the derivative. You can interchange the integral and the derivative. Now, another alternate way that you can actually approach this problem is through the Lebesgue dominated convergence theorem that you may have seen, that you may have encountered in measure theory. Okay, so you can also use this using Lebesgue dominated convergence theorem. Okay, so you have, so now what we have is that u of x comma t is actually smooth in both the x and the t variable for t positive, okay. Now the next part that I need to do is to show that u solves the heat equation. So I have shown that u is smooth. Next, let me show that u solves the heat equation. Okay, so notice that we have, so one thing that we have shown is the following, right? That the derivative, so through an application of the Lebesgue dominated convergence theorem, right? So we have that the derivative of u with respect to xi is the same as the derivative of this e power minus mod x minus that part over there with respect to xi. Okay, now recall that we have shown this theorem. We have shown this theorem that k of xt actually solves the heat equation in Rn cross 0 infinity. So therefore, what we can do is we can differentiate this e power minus mod x minus y the square by 4t with respect to the partial derivatives, and then sum up to actually get the Laplacian. And then you can also differentiate with respect to t. And then because you have already shown that the kernel satisfies the heat equation, we actually have that u also satisfies the heat equation. Notice that f here is independent of x and t, right? So no derivative. So no derivative is actually getting transformed, is getting into f. All the derivatives are either happening in this e power minus mod x minus y the whole square by 4t, or to this 1 over 4 pi t to the n by 2. No derivative is getting over here. But I have already shown that k of xt solves the heat equation. So therefore, you also have that u satisfies the heat equation. Okay. Now, one point to note is that we have not used the continuity. So I have not used specifically any property of f so far. Okay, except that I just need integrability. Okay, I need integrability, or in other words, I need to have the integrability over here. Other than that, I have not really used any part about f. Okay, so in fact, even for initial f in L1, so suppose even if the function f is in L1, the function u is still going to be infinitely differentiable. Okay, so we have shown that u of xt is infinitely differentiable, and I have used that f is continuous and f is also bounded. Okay, but I have not used other than boundedness, for instance. I have not used any other property because I just need integrability of that integral over there, but I have not used any other property. There is a part where I will actually use the continuity of f in a crucial way, but even for f in L1, okay, even if for f in L1, the solution u is going to be infinitely differentiable. Okay, all right. So finally, what we need to do is we need to show that u satisfies the initial condition f at t is equal to 0. Or in other words, what we need to do is we need to show that limit as t approaches 0 plus of u of xt is actually equal to f of x. So this is the part where we will actually use we will actually use three things. One is that f is continuous, that I will use. The second part is this following fact: limit as t approaches 0 plus of Rn minus Br of 0 of this kernel k of xt dx, that's actually equal to 0. So I will also use that part. And the third thing that I will actually use is that the integral over Rn k of xt dx is actually equal to 1. Okay, so all these three I will use and then see how it actually fits together in a nice fashion. Okay, let's see. So my goal is the following, is to show that U satisfies the initial condition f at t is equal to 0. And I'm going to use the fact that f is continuous. I'm also going to use the fact that f is bounded. Okay, so I'm also going to use the fact that f is bounded. Okay, so we need to show that limit as t approaches 0 plus k of x minus y t f of y dy, that's equal to f of x. So this is what I need to do. Okay, so the standard approach is what? So you consider the integral over Rn k of x minus y t f of y minus f of x. You take the absolute value, and then if you take t to be small enough, then you need to show that so given any epsilon greater than 0, there exists a t, there exists a small, let's say t naught, such that for every t less than that particular t naught, then this quantity is going to be less than that epsilon. So this is what I need to do. Okay, so let me consider, so with this in mind, let me consider integral over Rn k of x minus y comma t f of y minus f of x. But now notice that I have already shown that integral k of x comma t f k of x comma t dx is equal to 1. Okay, now by the same argument, you can also show that integral over Rn k of x minus y comma t, right, where x is some fixed. So you're just going to do a translation. Okay, so instead of, so earlier the peak of the Gaussian was at 0, but now it is going to get transformed to x. That's all. Okay, translated to x. That's all. Okay, so what we have, so the point here is that k of x minus y comma t dy, that's also the integral over Rn, that's also equal to 1. So therefore I can write, instead of this f of x, I can write this f of x times integral over Rn k of x minus y comma t dy. Okay, all right. So now this k, so now by the additive property of the integral, okay, so you can write this as integral over Rn k of x minus y comma t times f of y minus f of x dy. Okay, so that's exactly what I have over here. See this part, this is the left hand side, that's equal to k of x minus y comma t times f of y minus f of x, but that I again split it. Okay, now the way I'm going to split it is this r is going to be chosen later. Okay, but let me just split this part. Let me split this as Rn minus Br of x plus Br of x. So that's the sum is actually going to be the integral over Rn. So after splitting this up, now I'm going to observe. Now I'm going to take these two integrals and then see what happens. Okay, now one thing that let me recall what I showed is the following, that if you consider this, okay, if you remove a ball of radius r for any r, okay, doesn't matter. If you remove the ball of radius r centered at 0 and then consider the integral of k of xt in the complement of that ball, and then you let t approach 0, then the limit is actually equal to 0. Okay, now a similar argument would show you that if you consider the ball of radius r centered, so there it was centered at 0, but here it is centered at x. That's only difference. So if you consider the complement of the ball of radius r centered at x of k of x minus y comma t times f of y minus f of y dy. Now notice that f is bounded. Okay, so here is where I use the fact that f is bounded, right? And also notice that k is positive. Okay, so if I consider this part over here, so k is positive, so it's 1 over 4 pi to the t to the n by 2 e power minus mod x squared by 4p, so it's all positive quantities. Okay, but now limit as t approach 0 plus of k of x minus y comma t dy over integral over Rn minus Br of x, that goes to 0 as t approaches 0 plus. So therefore we have shown that this quantity here goes to 0 as t approaches 0 plus. So this is what I have written here. So we use the fact that f is bounded and that as t approaches 0 plus, this Rn minus Br of x, k of x minus y comma t dy, limit as t approaches 0 plus, that's equal to 0. Now for the second integral, so we have shown that this first integral that goes to 0 as t approaches 0 plus. We have already shown that. Now let me consider the second integral. So the second integral is integral over Br of x, k of x minus y comma t, f of y minus f of x. So notice that f of y, that is y and x, vary at most by r. Actually, vary at most by r, because x is the center point. So y and x vary at most by r. Now, what choice of r that I can take is under my control. What choice of r that I can take is under my control. Okay, so here is where I use the fact that f is continuous. Okay, so if I use the fact that f is continuous, you see that if I choose this r small enough, then this f of y minus f of x in absolute value is going to be less than some epsilon. Okay, so therefore now I can get rid of this f of y minus f of x bounded above in absolute value by epsilon. And then what I have is I have integral over Br of x, k of x minus y comma t dy. But this integral over Br of x, k of x minus y comma t, see k is a positive quantity. That integral that you know is at most 1. Right? Integral over the whole of Rn is equal to 1. So therefore the integral over Br of x, k of x minus y comma t dy is less than or equal to 1. Okay, it's actually strictly less than 1, but we don't need that. Okay, so that is less than or equal to 1. But f of y minus f of x is small. So this quantity f of y minus f of x, that is small. So therefore this quantity here, this integral over Br of x, by choosing r small enough, right, we have that this quantity here is less than the epsilon that you take, the epsilon that you started out with. So therefore I have shown that, what is it that I have shown? I have shown that integral k of x minus y comma t f of y dy minus f of x in absolute value is less than some epsilon, which is to say that limit as t approaches 0 plus. So limit as t approaches 0 plus of k of x minus y, or in other words, choosing t small enough, we have integral over Rn k of x minus y comma t f of y dy minus f of x is less than epsilon. Okay, or in other words, limit as t approaches 0 plus of k of x minus y comma t f of y dy, that's equal to f of x. So therefore I have shown that in the limit, it actually takes the value f of x. So what is it that I have done? What we have done is, using this representation, we have shown the solution to the heat equation ut minus, actually we have shown the solution to the initial value problem as for f being a continuous bounded function, f being a continuous bounded function. So therefore we have all the three parts, that is u is smooth. I have shown that u satisfies the heat equation, and I have shown that u also takes the limit value f. Okay, so now let me explain this infinite speed of propagation. Okay, so you can take your f to be a compactly supported function. Okay, but now what I want to do is you take, so since f is compactly supported and f is continuous, f is going to be bounded. Okay, but let me take f to be a non-negative function. Let me take f to be a non-negative function. Now, one thing to emphasize, if you go back to this particular representation for the solution, so if you take f to be non-negative, right, then your u is, so because this e power minus mod x minus y the whole square by 40, that is always, in fact, it is always positive. So therefore, this integral is always going to be non-negative. It's going to be greater than or equal to 0. But if you take f such that f is non-negative and f is positive somewhere, okay, because of the fact that this e power minus mod x minus y the whole square by 40 is always strictly positive, this u of xt is positive everywhere. It is positive everywhere. So let me just re-emphasize. So suppose you take f non-negative, let's say it's compactly supported, or in other words, you take f to be bounded, f to be continuous, f non-negative, but it is positive somewhere. Okay, it is positive. Otherwise, it's in other words, it's a non-trivial function which is non-negative. Okay, then what you have is that the u is supported everywhere. U is supported everywhere. Okay, so this is what we call as the phenomenon of infinite speed of propagation. So what we have is that this U of xt, the support of U of xt is in the whole of Rn cross 0 infinity. So this is what we interpret as the phenomenon of the infinite speed of propagation. So this is one important or one nice property that solutions to the heat equation satisfy. And that is actually what I wanted to emphasize. Thank you.